Welcome back, focus learners. You know, if you've ever used an AI to help you write a quick little Python script, you know just how magical that feels. Well, in today's explainer, we're unpacking a genuinely groundbreaking paper from Google Cloud AI Research that takes that feeling to an entirely new level. We are looking at a system designed to push the very boundaries of what artificial intelligence can actually accomplish in the realm of complex scientific discovery. Let's dive in. So it all starts with a pretty provocative question. Can AI automate its own research? I mean, we all know that large language models can write code, right? They can autocomplete a script, they can patch a simple bug, they can even build you a basic website. But architecting a complex machine learning pipeline from scratch, that is an entirely different beast, and we're going to look at exactly why that is. See, standard software engineering is often pretty binary. Your code either compiles or it doesn't. But machine learning engineering, or MLE, is highly probabilistic and incredibly resource-intensive. It requires an agent to process data, architect a model, train it, validate the results, and navigate a landscape where just evaluating a single idea might take hours of really expensive compute time. That brings us to Section 1, the AI research bottleneck. To really appreciate the solution, we first have to understand the problem. Current AI agents basically fail at independent research for three big reasons. First up, they write monolithic scripts. We're talking giant, single files of code that are fragile and practically impossible to debug. Second, standard search algorithms completely ignore computing budgets, so they might chase this tiny 0.1% accuracy gain, even if it turns a 1-hour training run into a 10-hour nightmare. And finally, they totally fail at credit assignment. If a model's accuracy suddenly jumps by 2%, human engineers will spend hours figuring out exactly why. Current AI, it often has absolutely no idea which specific line of code actually caused the improvement. Moving right along to Section 2, enter Mars. To bridge this massive gap in capability, we have a true paradigm-shifting solution. Coming straight out of Google Cloud AI Research, a team of top-tier scientists and engineers has proposed a fundamentally new framework. And this isn't just a minor update to some existing model. It's a complete reimagining of how an AI approaches research tasks in the first place. They call it MARS, which stands for Modular Agent with Reflective Search. So MARS is a framework explicitly optimized for autonomous AI research. Instead of just blindly generating lines of code, it smartly applies three distinctly human-like engineering pillars. We're talking modular construction, comparative memory, and budget-aware planning. And we're going to explore exactly how each of these three pillars transforms the AI's capabilities throughout the rest of this explainer. Essentially, Mars completely reformulates the entire research process. It doesn't treat the task as a text generation problem. Instead, it treats it as a search for an optimal software repository. The agent extracts the metadata, performs exploratory data analysis, and then iteratively loops through planning, modular decomposition, and reflective memory to evolve the best possible solution. It works just like a dedicated team of human engineers would when they're tackling a complex problem over several weeks. Let's move to Section 3, designing like a human. We can cleanly contrast the old way of doing things with the Mars way. The old monolithic approach is basically like trying to build a house by pouring solid concrete all at once. If you make a mistake, well, you have to tear the whole thing down. But Mars uses modular decomposition. It builds code like Lego blocks. By breaking complex tasks down into independent, testable blocks, the AI encounters way less context noise. It reuses code efficiently, and it localizes bugs instantly. Mars actually achieves this through a highly logical three-step pipeline. First, an idea generation agent drafts a natural language plan. Second, a modular agent decomposes that plan into separate files, like data loading, model architecture, and training loops. And third, a coding agent implements and debugs each module independently. Plus, it uses diff-based editing, which means it only updates the specific lines of code that actually need changing, rather than rewriting the entire project from scratch. All right, Section 4, learning from the delta. Remember that incredibly complex credit assignment problem we mentioned earlier? Well, to solve that, Mars relies on comparative reflective memory. As Mars explores different potential solutions, it branches out, essentially having a literal aha moment on difficult computer vision tasks. Instead of just reading error logs, it analyzes the exact delta, meaning the precise difference in code between a new solution and the previous best solution. By isolating that exact variable, it knows exactly what caused the performance shift, and it strategically caches that lesson for the future. And the data backs this up beautifully. According to the paper, a whopping 63% of all utilized lessons originate from cross-branch transfer. This is an incredible statistic, honestly, because it emphasizes that the AI isn't just blindly memorizing bug fixes. It is actively generalizing learned insights from one part of its exploration and applying them to entirely different ideas. Imagine if every time you fixed a bug, you inherently understood how to prevent it in every future project you ever write. That's exactly what Mars is doing. We actually have undeniable proof of these pillars in action through ablation studies. That's where researchers intentionally turn off specific features to see what happens. And the results are stark. Without modular decomposition or without its comparative memory, the agent's performance completely flatlines over time. Without these fundamental, human-like engineering principles, it literally just stops progressing altogether. Which takes us to Section 5, budgeting for success. Just like a human engineer working for a company, an AI has to balance the cost of an experiment against its potential performance. Mars does this using budget-aware planning via a Monte Carlo Tree Search, or MCTS for short. In simple terms, it maps out different future scenarios to see which path yields the best possible result for the lowest cost. It effectively penalizes computationally expensive solutions to make sure it doesn't just burn all its allocated time and money chasing a tiny fraction of a percent of accuracy gain. You can actually see this efficiency check happening in real time. When Mars is presented with several candidate models that all have very similar validation accuracy, the efficiency-guided reward literally forces the agent to choose the faster candidate. It actively prunes inefficient ideas, saving all those valuable compute hours for further exploration down the line. Finally, Section 6, winning the gold. So, we have the theory and we have the framework, but how does this thing actually perform in the wild? Well, to prove its worth, the Google Cloud researchers submitted Mars to the ultimate proving ground, MLE-Bench. This is a benchmark designed specifically to test how well AI agents can perform on highly complex, real-world machine learning engineering tasks. And let me tell you, it is an absolute gauntlet. The agent is forced to compete across 75 real Kaggle competitions. It's given a strict 24-hour wall clock time limit per competition, and it's constrained to a standard A100 GPU compute setup. It has to prepare the data, do the feature engineering, train the model, and submit the inference all completely autonomously. So the crucial point here is this number, 33.8%. When scaled up to a dual GPU configuration, Mars Plus achieved an incredible 33.8% gold medal rate on these grueling Kaggle competitions. It also achieved a 62.7% any medal rate. To put that into perspective for a second, that absolutely crushes the existing open source competition, setting a totally new state-of-the-art benchmark for autonomous AI. But of course, this raises a massive question, right? Did the AI just memorize public Kaggle notebooks from its training data? The researchers actually tested for that using plagiarism detection tools. The similarity distribution shows that Mars engineers highly original solutions, with no submission exceeding a 60% similarity threshold to public code. So it's not cheating, it is actually doing the hard engineering work itself. Which leaves us looking at a truly fascinating horizon. By structuring AI code generation like a professional engineering repository, complete with modular design, memory, and budget awareness, Mars has solved a massive bottleneck in the field. If AI can now reliably engineer its own optimal machine learning solutions, what frontier of scientific discovery will it automate next? It's definitely a thrilling thought to end on. Thank you so much for joining me for this explainer. Keep learning, and I will catch you in the next one.